I was thinking about some of my favorite things the other day, and yes, it included NMR spectroscopy. And I was thinking in particular about one of the most common types of questions that chemistry students are going to encounter when they start learning NMR spectroscopy, and that is the old pick the structure out of the lineup problem. We'll give you a spectrum, we'll give you a series of possible structures that would match that spectrum, and your job is to figure out which one it is. And I was doing this with some of my students earlier this semester, and it was interesting. It's always interesting to watch students as they try to approach this type of stuff, because let's face it, learning NMR is difficult. My favorite analogy is learning NMR is like learning how to drink out of a fire hose. There is just so much information involved that it's really difficult to learn how to sort through. And I had students Googling things, and they had pulled up some of the world's most complicated chemical shift tables and were trying to pick out various things. I had others who had looked up, websites about, nuclear coupling constants, and were looking at bizarre patterns like these and trying to make sense of them. And, students just, trying to do all kinds of different things. I guess sometimes students find, learning NMR, drinking out of a fire hose, to be just virtually overwhelming, and just don't know where to begin. And really, for a task like this, for just simply pick a structure out of a lineup type problem, really, I honestly believe you need to only think about your 5 best friends when you're dealing with this type of problem, when you're being introduced to NMR spectroscopy, especially proton NMR spectroscopy. There's really only 5 regions that will get many of these types of problems answered pretty readily. It ought to solve at least 80% of them that you're likely to encounter. And so I want to emphasize these 5 regions, what they tell us about. They give you an example that I was using in my class, and it was simply, I told the class that the spectrum I gave them was an over-the-counter pain medication. Well, which one was it? And we'll run through all that in just a moment. But here are your 5 regions. These are the 5 that you really need to look at carefully. Okay? So here they go. First, the aromatic region. The area of a proton NMR spectrum between about 7 to 9 ppm. It can be outside those ranges just a little bit, but this is generally the area you find the hydrogens on an aromatic ring. And the integrations will also tell you the number of substitutions generally on an aromatic ring. This is a great area to look at, okay, because not much else comes here. If you see peaks around 7.5 ppm, it's almost certain you have an aromatic molecule. Okay, there may be exceptions, but that's generally good rule of thumb. Okay, so of the 5 best friends, number 1, the aromatic region. Second best friend, the alkene region. This is about 5 to 7 ppm. This is where hydrogens sitting on a double bond are going to show up. Okay, now there can be other things in here, but alkene is by far the most common. And so if you see especially interesting splitting patterns in this area, that is a great characteristic of an alkene. Third best friend to look at, hydrogens near electronegative atoms. If you're a hydrogen on a carbon that is attached to an oxygen or to a nitrogen, that would be found, say, a hydrogen found in an ester or an ether or an alcohol or an amine or an amide, something like that. Okay, the area around 4 ppm is very common for hydrogens like these, and it can vary, from like 3.6 up to 4.5, somewhere in there. But the zone around 4, okay, tends to be hydrogens near electronegative atoms. Also a very diagnostic area to look at. Then there's the 4th best friend, the shielded methyl groups. Okay, the area around 1 ppm, from about 0.7 to about 1.5. Now, methyl groups can be in a lot of different places, even around 4. Okay, a methyl group right on an oxygen, say, and a methoxy group is going to show up, around 4 ppm. But I'm talking about the shielded ones. I mean methyl groups that are at the end of a chain, a CH2, CH2, CH3, something like that. They tend to be down around 1 ppm. And there's not much else that comes down here, so it's a very diagnostic or very, interesting region to look at. Okay? The fifth best friend you have are broad peaks. Now they can be in a lot of different places. They can be from the most de-shielded to, some of the most shielded peaks in an NMR spectrum. But they have a characteristic. They're usually broad, sometimes so broad that they almost disappear into the baseline. By broad, I mean, they're just peaks that are fatter than the other ones around them. This is almost always a hydrogen on an oxygen or on a nitrogen, okay? Like, for example, the hydrogen of an alcohol or the hydrogen on the nitrogen in an amine will often be broad at peaks. Now, again, the positions are very dependent upon the solvent and how wet the sample is. Carboxylic acids can be all the way down at 12 ppm. Alcohols in a dry solvent or something can be down closer to 1.5 ppm. But they almost always have the characteristic of being broader peaks than the others around them, especially hydrogen sitting on a carbon atom. And so broad peaks are really something that is fairly easy to spot and good to look for. So your 5 regions: the aromatic region, 7 to 9 ppm, the alkene region, 5 to 7 ppm, hydrogens near oxygen or nitrogen around 4 ppm, and near oxygen or nitrogen, chlorine would be as well. Hydrogen on a carbon on a chlorine or a fluorine would work just as well, around 4 ppm. Shielded methyl groups around 1 ppm, and then broad peaks, hydrogens on an oxygen or on a nitrogen. Those are your 5 best friends, and they can answer an awful lot of questions without having to resort to long tables of chemical shifts or coupling constants or any of the other sort of stuff that students sometimes like to get tangled up in. So, what I did is I gave my students a proton NMR spectrum. Here it is. And I said, this is an over-the-counter pain medication. Okay? And I directed them to things like, the compound interest website, which has a lot of great graphics on a lot of different things, including painkillers. And this is the one that they were looking at, and it has a lot of the common opioid painkillers that you hear about these days. But I said the one that we were looking for is an over-the-counter one, and that meant it was restricted to these 3 molecules here. And so I wanted them to be able to tell me if the spectrum that I'd given them was from aspirin, was from acetaminophen, or was from ibuprofen. Okay, these are the 3 most common of the over-the-counter pain medications. And so what I want to do is I want to look at the structures of the 3 molecules and look at our 5 best friends and see which one of these 5, which ones of these 5 we can use to tell the difference between these various molecules with a quick glance at the NMR spectrum itself. So, first up, the aromatic region, okay, 7 to 9 ppm. We look at all 3 of the structures of aspirin, acetaminophen, and ibuprofen, and we see that they are all aromatic molecules. Furthermore, the aromatic regions, there are 4 hydrogens in each of these aromatic regions, and so we should see peaks. They're in the 7 to 9 ppm region, integrating to 4. And sure enough, our proton spectrum shows that. That's very nice, but that by itself doesn't tell us which one of the molecules. There's all 3 of the molecules would have something similar. So that one doesn't allow us to tell the difference yet. But on to the next. Alkene region, okay, the area around 5 to 7 ppm. Now, none of our molecules are an alkene, and we look at the 5 to 7 ppm range, and sure enough, we don't see anything in there. Doesn't tell us, again, which one our molecule is, but it is consistent. So far so good. On to our 3rd best friend. The area around 4 ppm. Hydrogens near an oxygen, nitrogen, or other electronegative atom. Now, we look at the 3 structures, and we see oxygens and nitrogens, but we don't see any hydrogens on a carbon directly attached to the electronegative atom. We do see, like, for example, a carbon attached to a nitrogen in aspirin here, but that carbon is either a carbonyl on one side or the carbon of an aromatic ring on the other. Neither one of them has hydrogens on that. So none of these structures are going to have peaks right around 4, and sure enough, we don't see anything. We see something fairly close, but nothing right around 4 ppm. So that one's let us down as well. Then we get to the shielded methyl groups. Here is where the real differences start to show themselves. It is true, all 3 of these molecules have methyl groups in them, but only one of them, the ibuprofen structure, has methyl groups that are far away from the rest of the molecule at the end of a CH2, CH2, CH3 chain, for example. And these shielded methyl groups are very different from the methyl groups we see in either the acetaminophen or in the aspirin, where in both cases they're methyl groups right next to a carbonyl. Okay? And sure enough, when we look at the proton NMR spectrum, boy, do we see peaks right around 1 ppm. In fact, we see, peaks that integrate to a total of 9, 6 of them here at 1 ppm, and another 3 over here at 1.4 ppm, okay? Which would indicate 3 methyl groups, total of 9 hydrogens. And sure enough, ibuprofen has that in spades. So right there's the evidence we need that the 3 possible structures, it was ibuprofen. There's just, no doubt about that now. We look at our 5th best friend, however, and we look at the broad peaks, and we do see one. There is actually one out here at 12 ppm in this sample, which is consistent with ibuprofen. This is where a carboxylic acid would here. It is such a broad peak, it's almost a little bit hard to see in the baseline sometime. Now, we look at the structures of the other 2, and they both have hydrogens on an oxygen. In the aspirin case, it's a phenol, and in the acetaminophen case, it is another carboxylic acid. This is probably seeing our spectrum with a peak around 12 ppm is enough to eliminate the aspirin, but it's not enough to be able to tell the difference between ibuprofen and acetaminophen. But combined with the evidence from the shielded methyl groups, there's just no doubt this molecule is ibuprofen. Okay? So like I said, those 5 regions right there, aromatic region, alkene, area around 4 ppm, hydrogens near an electronegative atom, shielded methyl groups around 1, and your broad peaks wherever they may show up. That is often enough to be able to pick out from a list of possible structures and one spectrum what molecule it must be. Okay, and so there's, in an attempt to try to prevent people from just becoming too overwhelmed with the amount of information in NMR spectrum, keep those 5 in mind, because it will often be able to get you through a lot of the initial learning about how to interpret NMR spectra. Hope that helps. Talk to you later.